Computer. Okay, welcome back, everybody. We're here at our organic chemistry class, and we're going to continue on with chapter 5, which is stereochemistry. So stereochemistry is one of those challenging things for a lot of people because it's 3D spatialization. So it takes practice, which is why we're doing the activity on Friday afternoon. So what we're going to do is we're going to get through today is how to do chirality of a single center, which we started with on Monday. And we're going to continue that on how to classify things as to which chiral component you have in your set. And then we'll also show you some rules associated with that. Then on Friday, we're going to continue on with the lecture and talk about more than one stereocenter, and then we're going to have our activity in the second half. The activity in the second half is going to be assigning R and S to a bunch of different compounds, plus we're also going to add assigning E and Z to a variety of compounds. The cool thing is the prioritization we use for E and Z and the chirality is the same. So we get to use those same 3 rules, and I'm going to go over those again today, so that we can use those to both of our types of stereochemistry use those same rules. Okay. So for our let's see, we have the slides are available on Canvas and on Top Hat here. We're at our Zoom meeting. I'm looking at my administration. It says right here the homework, which is the reading assignment. No, the homework is the reading assignment. There's no separate reading assignment. No separate homework. So as you're reading through the book, you answer those questions, and then you can get up to 20 points for that if you answer all of them correctly. You have a couple different chances to get there, so you can try a couple things, read it again, try once. If it's not right, read it again, and see if you can get it right the second time. So that's what our homework is going to be this week. I'm trying this out to see if you like it better. It's also encouraging you to make sure you do read the book, because there's some details in the book that I can't get to in class. And so it makes it really good for you to reinforce the book with the lecture and our activities to get a really good handle on this topic. Okay. I might extend the deadline for the homework to next Wednesday, because we're not going to be completely done with Module 5 until Monday. So I'll look for that to move to Wednesday of next week as its due date, so that reading will be assigned for that. Okay, any questions about administration up to this point? Okay.
I was going to ask if we're going to get the group activity like last time, or if we're just going to get it on Friday.
Yeah, you're going to get it on Friday. I'm going to email it out Friday morning, as well as I'm going to post it on Canvas Friday morning. And then just like last time, it will be, you need to upload it to Canvas by midnight. Okay. So that is what we have for that. And so what we're going to do is we're going to go ahead and share my screen. Let's see if it's going to do it. Yes. All right. So this is where we left off last time. We were talking about the importance of chiral centers in biology. And so it's not only that in biology. One of the great things about the chiral centers in the biology is that when your body makes a specific isomer, okay, it only makes one. So you can have a molecule like a steroid, cholesterol, for example, that has about 10 stereocenters in it. And so that means there could be like 250 different variations of that particular compound, but your body only makes one. Makes every stereocenter exactly that same way. And that's the great thing about the biological aspects of the stereocenters. But we're going to talk about one stereocenter at a time to start with, just so we can get a handle on what chirality is, how it's defined, how we can identify the 2 different isomers possible, and how we classify them. Okay. So moving on from where we started yesterday. Now, just because something seems to be chiral, i.e. seems to have 4 different bonds to it, We can actually ruin chirality or make it achiral, not chiral, by having a plane of symmetry, okay? So in this case here, if we have a plane of symmetry, like we saw in the previous sample where we put a plane through the middle of a molecule, and we saw that one side looked exactly like the other side, proving to ourselves that that was not chiral. We can do this not just through bonds themselves, through atoms themselves, but also through bonds. So for example, here, if we put our mirror in the middle here, we have a CH3 that's up that looks exactly like the CH3 on this side. We have each of these carbons that look exactly the same. Because we can find this mirror plane, this plane of symmetry in the middle here, it makes this compound no longer chiral, okay? So we actually have a chiral center here and a chiral center here. And both of those chiral centers, because of this plane of symmetry, now no longer have chirality. And it has a special name when we do this. It's called a meso compound. And we're going to talk about that again on Friday. Okay, so here's another example here where we have a chiral center here and a chiral center here. And if we look at it, you know, these methyl groups are, you know, mirroring each other. These hydroxides are both sticking out at us. That's that solid wedge. They're both sticking out at us, and they are mirrors of each other, and the hydrogens are. But because we have that mirror, that means the chirality of these two centers then cancels each other out, and it becomes achiral. Okay. Now, we can also find a plane of symmetry through things like, notice it's going through a total of 4 atoms right here. It's going through this, the carbon and this oxygen here, meaning half of that oxygen is on each side of that mirror, and that still counts as a plane of symmetry, and therefore all of these compounds are meso compounds, or compounds that have stereocenters, like 2 stereocenters, but do not have chirality because of a plane of symmetry. Okay, and we're going to do that again on Friday. Okay, so let's talk about simpler systems. Let's talk about a compound, and we're trying to see if it has a chiral center, okay, or if it has a chiral atom. Now, the first thing we need to look for whenever we talk about chiral centers is the idea that you typically have it as a carbon, although it can be nitrogen in some cases. We look for the carbon and we count how many different groups it has on it, okay? So it has to have 4 different groups to be chiral. If 2 of the groups are the same, we can find a plane of symmetry where those 2 groups are the same. Therefore, we have to have 4 different groups attached to a carbon. And if we do that, then we can start to think, okay, this might be a chiral carbon. Let's look and see what we have, okay? So that also means that only sp3 hybridized carbons can be chiral carbons, okay? Because only sp3 hybridized carbons are tetrahedral, and only the sp3 hybridized carbons can have 4 things attached, okay? Now, what this also means is all CH2s and CH3s are not chiral. So again, we need to start, the first thing we do is look for 4 different groups here. Okay, so let's look for 4 different groups in this first molecule here. Now we have a bromine here. We have a CH2CH3. Okay, well that kind of looks like this one here. Oh, but this has a CH2CH2Br. So that's different, okay? And this has a CH2CH2Br. That means that those 2 groups are the same, right? So this is not a chiral carbon, okay? Notice we had to go and all the way out to here and compare these 2 sides to say those are identical compounds. Therefore, you have to look at the entire chain that's attached to that chiral carbon, okay? And see if there's any differences there. So being that, if we were to take this material right here and go ahead and say, well, let's just see, let's draw its mirror image. So if we put a mirror here and we started from here, we go to a bromine, and then the CH2, and then the carbon, and then the central carbon, and then the CH. And then notice the wedge here comes out here, and the bromine is back here and back here. So just by going from the center out, we've been able to draw our mirror image of it, okay? Now, the problem with this mirror image is if we take this and rotate it around such that we move this bromine where this bromine is, so we just rotate it around by approximately 120 degrees, we'll see, so if we take this image and rotate it around, it looks like this. So we've rotated this bromine to here. Now notice that when we look at this molecule and this molecule, they're identical. They overlap because we've created the mirror image and they are now superimposable. They are no longer chiral. Okay, so we have to have 4 things bonded to carbon. We have to have a mirror image of those chiral, of that compound, and that mirror image cannot be superimposable. Okay, so let me demonstrate that on this next one here. Okay, so on this next one here, let's change colors here. So all we did was we swapped out one of these groups here with a methyl group here. So now we have a bromine, a methyl group, an ethyl group, and an ethyl group with a bromine on it. Okay, that's 4 different groups. We think it might be chiral. Let's go ahead and prove it to ourselves by drawing its mirror image and seeing if it is superimposable or not. Okay, so let's do that exact same structure of making a mirror image. And again, the way we do our mirror image is we start from the mirror plane we have here. We have H's are the same, the carbon's the same, this bond and this bond is the same, this ethyl group is up here, just like it. So see how we're mirroring those images there? And they're just starting from that mirror plane and working our way out. By doing this, starting at the mirror and working our way out, we always get the right mirror image because we're not tempted to swap any groups. Okay, so let's continue on drawing our mirror image here. And so now we have this group, and notice they're both have this solid wedge, so they're both still sticking out at us. And notice how we drew it so the bromines were actually sticking away from each other. So we have a perfect mirror image of those. And this other bromine has the dashed wedge, meaning it's going behind the plane, and we draw it again as the dashed plane. Okay. So now we have correctly drawn our 2 different isomers. And so this pair of 2 different isomers are what we call enantiomers. Enantiomers are the one chiral molecule in the mirror image, non-superimposable mirror image of it. And enantiomers always come in pairs. So if you have one enantiomer, you can draw the second enantiomer. They always come in pairs. Now, let's prove that they're chiral by rotating it around and seeing if they are superimposable. So the next thing we do is we take our compound here and we rotate it such that our, our bromine here has to rotate back around here and be a wedge on this side. So if we rotate that bromine 120 degrees, that means that this has to rotate 120 degrees and this has to rotate 120. Notice that we're using this as our axis. This is where it's rotating around. So you can imagine you have your compound sitting on a tabletop and all you're doing is rotating at 120 degrees so that the bromines line up on both compounds. Okay? So if we did that and we redrew this so that this is moved over 120 degrees, so it's in the plane of the paper here, we see that our methyl group, our ethyl group, and our carbon are where they were, because that's the axis we rotated on, okay? The only thing that moved was this methyl group came out and became our solid wedge. This bromine moved back and became our dashed wedge over here, and this has to be our other one, which is in the plane, so it's just a straight line, okay? So now let's look at these 2 images and see if they are identical or not. So if we look at this image and this image here, we have the ethyl group and the carbon here. Okay, that matches. We have the bromine and the bromine. That matches. Uh-oh, they might be superimposable. Oh, wait, hold it. This methyl group is not an ethyl group with a bromine on it. And this methyl group is not an ethyl group and a bromine on it. So that means those two groups have swapped, and therefore they are not superimposable. If they are not superimposable, and it's a mirror image, these are mirror images of each other because we just drew it, and all we did was rotate it around. Now we have a pair of enantiomers, two, and one's going to be one configuration, and we're going to talk about how to identify the configuration next, and the other one's going to be the other configuration. So chiral things have 4 different groups on them. They come in pairs. Those pairs are mirror images of each other that cannot be rotated and superimposed on each other in any way. Okay, and what the chiral actually means handed. Okay, so most people have 2 hands, and if you look at your hands, they are mirror images of each other, right? And so if you try to superimpose, so have the back of one hand over the back of the other hand, they are mirror images of each other, but they don't match because we have, you know, a thumb is going to be covering a finger, or a finger is going to be covering a thumb, or the thumbs are going to stick out to the side. They are not superimposable. Okay, so we have mirror images here, but they are not superimposable. Okay, and even if we did it like this, we have the top and bottom matching, so we need to get the bottom and bottom aligned, or the top and top aligned. And at that point, they're non-superimposable. So that's the way to think about enantiomers, as a pair of non-superimposable things. And in chemistry, we look for those carbons, or sometimes nitrogen, that have 4 different groups. Okay. So, and it takes very little to take something that's not chiral and turn it into something that is chiral. For example, on this last example here, okay, we have 1, 2, 3, 4 different groups right here. All we have to do is remove one methyl group, or one methylene group here, from this chain, and they become the same, and therefore this is not chiral anymore. So one small change in one of the chains is enough to change it from being a chiral system to an achiral system. Okay, so that's why you got to look at, make sure those 4 different groups are truly different all the way down the chain. Okay, so now I said that they come in pairs, okay? And those pairs have different names. We have, remember, our nomenclature system is very precise, okay? We do that preciseness in our nomenclature such that if I write down a name, you can draw it, and somebody, you know, 1,000 miles away can draw the exact same compound. So we have to have that same precision when we're talking about these enantiomers. They have all the same atoms. They have all the same connections. The only difference between the two is where they are in space. Okay, that's what the stereo part of stereochemistry is, their position in space. Okay, so our nomenclature system for this pair of enantiomers is what we call the R and S system. So one is going to be what we call rectus, and one is going to be what we call sinister. So one is going to be right, and one is going to be left. Okay, and so we have to decide how to assign R and S. Okay, so we have a way of doing this, and we call it the Kahn-Ingold-Prelog method. And basically, we use the same priority system we used in assigning E and Z, but we apply it to 4 different groups on the same carbon, instead of just one half of the alkene and the other half of the alkene. Okay, so what we're going to do is we're going to assign the exact same way. The first rule is we assign by atomic number, not atomic mass, atomic number. Okay, so the highest atomic number has our highest priority. Our lowest atomic number has our lowest priority. So if you have 4 different groups attached to your thing and they all have different atomic numbers, you're done. Okay, you only have to use rule 1. Okay, so if you can assign the system using just number 1, the first rule, then you are done at that point, and you can start assigning whether it's R or S. However, most of the time we end up with a situation like we have here. So we have oxygen here, which is atomic number 8. We have hydrogen here, which is atomic number 1. And we have 2 carbons, both atomic number 6. Okay. So we can only assign priority to 2 of these groups right now. We can assign this as 1, and we can, this is 1 because it's our highest priority, our highest atomic number. And this is number 4 because we have 4 groups, and it's our lowest atomic number. But now we can't assign the carbons because they have the exact same number. So what do? We have rule number 2. Rule number 2 is if you can't assign it with rule number 1, now we go on to figuring out what else is available to us. So if we compare just this carbon with just this carbon, let's look at what's attached to it. So if we have this carbon here, we only have a hydrogen, a hydrogen, and a hydrogen, okay? Each of those have the atomic number of 1, okay? If we look at what's attached to this carbon, we're gonna put the highest priority thing attached to it first and then go down in order. So in this case here, we have a carbon attached to it, which is number 6, number 1. And so between these two, because we have a higher number of attached to this carbon than attached to this carbon, we have this higher atomic number atom attached to it, it becomes the higher priority item, okay? Which means that this group right here with the ethyl group is now our 2, and this methyl group is our 3. So now we've used our rule number 1, which is just atomic number, and rule number 2, okay, let's attach to 2 things that have the exact same number. Okay, so those are those first 2 rules, and those are the same rules we used for E and Z. Okay. Now, once we've assigned priority, now we can assign R and S, okay? So we have 1, 2, 3, and 4 assigned, and all we have to do is to make sure we are looking at this correctly. We always move it so that the number 4 priority is sticking away from us, okay? And when we have number 4 priority sticking away from us, we look at it as a clock face, okay? And then we assign our priorities and we say, is that going from 1 to 2 to 3, is that clockwise or is it counterclockwise? Okay, so this is the molecule we started with. We have that hydrogen here, but that's not good because that hydrogen is facing out away from the page. We actually have to rotate this 120 degrees. When we do that, that means this OH comes out here and this methyl group comes out here. So if we rotate that, what we end up with is this compound here. Right here. It's the exact same compound. All we've done is rotate it 120 degrees. Now, our hydrogen, or our lowest priority thing, is behind the page. Everything else is coming toward us or in the page. Now we can assign priority. And the way we do that is we look at the numbers in order, 1, 2, 3. And if the numbers in order are going in a clockwise fashion, then we call this rectus, or right. So it's turning to the right, and therefore it's clockwise, therefore it's R. Okay? So now, if our priorities were going the other way, if this ended up being 2 and this was 3, okay, let me change that. If instead our priorities were different, such that this was 2, and this was 3, we would be going 1, 2, 3, and that would be going counterclockwise, and it would be S, meaning from the Latin sinister, or left. Okay. So do we see where the R and the S come from? Do we see that R is related to getting 1, 2, and 3 in a clockwise pattern? And do we see that S is getting 1, 2, and 3 in a counterclockwise pattern? And remember, 4 is always facing away from us so that we can get that perspective correct. Questions on that? Okay. All right, so let's do a little bit more with this, okay? So now we have the basic idea that we have 4 groups. We assign their priority based on their atomic number. If we can't assign it by atomic number, we move one bond out and assign it to the thing with the highest atomic number attached to it. Okay. So let's go ahead and do this same thing. And we've already assigned the RNS to this particular molecule here. And again, when we first drew it, we drew it like this right here, but we had to rotate it 120 degrees on one axis to get us to allow us to do our 1, 2. We had to rotate it. Oh, that's our mirror image, sorry. Okay. So if this is our 1 enantiomer, this is our R configuration, that means there must be an S configuration to match the pair, right? Enantiomers always come in pairs. One is always going to be R, one is always going to be S, okay? So let's figure out how to get to the other compound. Now, when I showed you that thing before, enantiomers always come in pairs and they always have a mirror plane. So let's draw the mirror image of the one we've already assigned as R and see if we can determine whether it's S or not. So in this case here, notice our hydrogen is first, our methyl group is still back, and our oxygen is here, and this is our other chain. So we've mirrored our image. And so now we can start our assignment. And our assignments should be the same priorities. It's just they should be in different places in space, okay? So our methyl group is still gonna be our priority 3 because it's only bonded to hydrogens. Our ethyl group here is gonna be priority 2 because of that carbon. And our oxygen and our hydrogen here are still gonna be 1 and 4 because of atomic number. Okay. Now, can we use this version of the thing and decide whether it's R or S? No, because we have to have number 4 away from us to get the perspective correctly. So to do that, we need to rotate this hydrogen back to the back by rotating it 120 degrees. Okay. When we do that, we end up with the OH on this side because it's coming around. This is going around. And that methyl group is going to end up on this side with our hydrogen back here and our other group here. This is the axis we were rotating on. So we still have this is our 1, this is our 2, this is our 3, and this is our 4 that we had before. And now let's go and see whether it's R or S. Now that hydrogen has been rotated to the back. We have 1, 2, and 3, and that is counterclockwise, which means this must be the S isomer of the compound. Okay. So whenever you have one enantiomer, you draw the mirror image of the other. It should be the other configuration. Okay. So let's look at those 2 molecules and we're going to reorient them the same way. So this one right here, we've rotated that 120 degrees. So this is what it looks like now. Okay. This one we've rotated here and we now have it in that same perspective with the number 4 priority back. And if we look at our rotation, we have 1, 2, 3 going in a clockwise. So this is our R. We have 1, 2, 3. This is counterclockwise. This is our S. Okay. So when you're assigning your R and S, you must have your priorities first, and then rotate your molecule, preferably either drawing it or something else, such that your number 4 priority is in the back. And when you do that, you now can do clockwise or counterclockwise to assign R or S. Questions? The carbon with the oxygen, the methyl group, the ethyl group, and the hydrogen is the chiral carbon. It's the chiral center, it's the stereo center, and both of these compounds are chiral. Remember, all chiral compounds come in a pair, and that pair is that pair of enantiomers. One is always R, one is always S, and it's always a pair. You may only get one, but by drawing the mirror image of it, you can draw the other version of it. Okay? Okay, so we're going to do this a lot on our activity on Friday as well. Okay, so now there's a complication, is that sometimes just looking at what's attached to it doesn't really work that well because we have double bonds or triple bonds. Okay, when we have double bonds or triple bonds, we have to use rule number 3. Okay, so rule number 1 was atomic number, and if atomic number identifies it, then you're done. Rule number 2 is if you have two things with the same atomic number, you have to go and see what's attached to them. And the one with the highest atomic number attached to it has the higher priority. But now we have double bonds. Now we have to assign those priorities associated with those double bonds. Okay? And the way we do that is we do what we do first, is we look at the different atoms and see if we can assign them by number 1. Okay? So if we look at this, let's go back one. If we just look at this compound, let's assign it using rule number 1. So nitrogen here, nitrogen is atomic number 7. This is a carbon, atomic number 6. This is a carbon number 6, and this is atomic number 1. So we can assign 2 of the groups right now just using number 1. Okay, so let's do that. And so we're going to have, this is going to be our priority 1, and this is going to be our priority 4. Okay, so now we have to compare these two right here. Okay, and so what we have is our complication as we have a double bond here. How do we handle that? We handle that with group 3. And the way we handle that is we count each of those bonds as bonded to that atom. Okay, so that would mean this carbon right here is attached to an oxygen, this one, an oxygen, that one, and an oxygen, the second bond to this atom. So this carbon has 3 oxygens attached to it because it has 3 bonds to carbon. Let's look at this carbon right here. We have an oxygen attached to it, and then we have a hydrogen and a hydrogen. Okay, so now we have one with 3 things that have atomic number 8, one that has 1 thing with atomic number 8 and 2 things with atomic number 1. Therefore, this is our higher priority. Okay, so let's look at that again with color graphics. Okay, so because we could assign these 2 just by atomic number, we're done. We don't have to do anything more there. Because these were both the same atomic number, we had to look what was attached. Okay, now when we looked at what's attached, we used rule number 2 to assign this one right here as having 1 oxygen and 2 hydrogens. But we had to use rule number 3 to assign this triple bond, which gave us a designation of oxygen, 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 and that makes it the higher priority atom. So 1 and 4 were assigned by rule 1, 3 was assigned by rule 2, and the last one had to be assigned by rule number 3. Okay. So now we have our priorities. Now we can actually measure R and S. Okay, now we're really fortunate here because the way it's drawn, our hydrogen is already facing back. So we have our 1, our 2, and our 3. And so that's going in a clockwise fashion, which means this is the R isomer. Okay, so do you understand rule number 1, rule number 2, and rule number 3? Okay, because these are the 3 rules we'll use to assign priority. Once you assign priority, you use clockwise and counterclockwise, or yeah, that's in your perspective, to assign R and S. Clockwise is R, counterclockwise is S. Okay, so, and it looks like we did completely assign this correctly because we had our 4 in the back right, and we had our clockwise position, which designates it as our R isomer. Okay. No, not that. Okay. So that is one way to draw them. Okay. Now, because we all have a different perspective on how things are, we can draw these in the same isomer, the same S isomer in these 12 different ways. You might be able to draw more, but notice we have a couple different perspectives. And I want to draw your attention to how to draw things. It would be best if you, when you're doing chirality, to draw it the exact same way every time. So choose one method and then do that. So this is a very common method right here. And when we do this, we call it the tabletop. So you set it on the tabletop, 3 of the atoms are touching the table, and one of them sticking up. And typically that one that's sticking up is the one you want to rotate things around, okay? So, but in this case, right here, it makes this difficult to assign priority. So wouldn't it be easier to draw it in this configuration here, because the hydrogen's already facing back, and we can assign our priority of 1, 2, and 3, and we'll have our counterclockwise right there, telling us we have our S isomer. Okay. So another way to do it is to draw it where you have this perspective here. Notice that these atoms right here are in the plane of the paper, and the 2 at the top are coming in and out of the paper. So you can redraw that so that hydrogen's going back, and again, get that S configuration. The last way to draw it is one of these right here. It's the plus form right here. And whenever you have a plus form, you always have 2 things going back, 2 things coming forward, because the carbon at the center is the only thing in the plane of the paper. Everything else is coming out or going back. And you can also use this to help you assign, because especially when you have at least your hydrogen or your lowest priority back, you can go 1, 2, 3. And if we're looking at it from the top down, we're going counterclockwise, and therefore it's the S configuration. So it might be good practice for you to look at all these different things and make sure you can assign all of them as S, looking at the priority and trying to rearrange it so the hydrogen is facing back, so you can get that good clockwise perspective to give you that correct designation of S for each of these things. Okay, questions on that? Again, these are all the exact same compound. So they're just all drawn in different ways. Okay, all right, we'll move on. Okay, so now we know that a chiral compound is something with 4 different things bonded to it, and we know that we have 2 different possible copies of it, because when we make the mirror image, they are non-superimposable, and therefore they are different compounds in spatial arrangement. Everything else is identical. Empirical formula, connections, bonds, bond orders, everything's the same except for these. Now, that being said, because these all have the exact same bonds, they tend to have the exact same melting point, exact same boiling point, exact same density, okay? The only way we can tell them apart is that one will rotate light clockwise and one will rotate light counterclockwise, okay? So let's talk about that experiment here. So most light, as it comes out of a light bulb or whatever, has, light is a wave. So it has a directionality to it that's going in one axis, okay? But when it comes out of the light, they're all going in all the different directions, because there's no reason for them to do that. It be aligned. Now, if you take a filter and the filter only has a slot going in one direction, and you have all these light going in all these different directions, you can actually filter out everything that doesn't go through the slot. What that means is that all the light coming through that slot is now aligned in the same order, okay? We call this plane polarized light, because they're all in the same plane. They're all going exactly the same, and none of them are counter to each other, okay? Now, if we have this plain polarized light and we have a solution with a chiral molecule in it, that chiral molecule will react with these planes of light and will slowly start rotating them, all of the light in one direction or the other. And so this rotation of light as the going through the sample is what we call optical rotation, okay? And if a molecule does this, it's called optically active, okay? And typically only chiral molecules are optically active, okay? Now, this is a very interesting thing because this is the only way to tell them apart, okay? We can draw them as RNS. We can take their melting points, they'd be exactly the same. The only way we can tell the difference is that one will rotate the light one way and one will rotate the light the equal and opposite direction, okay? So how do we measure this? We measure this using a thing called a polarimeter. It's a device with a light source that gives us all our light, a polarizer, which turns all our light into the same plane, the sample cell that we're going to dissolve our material in and shoot the light through, and then another filter at the end to help you figure out how far it is rotated one direction or the other. Okay? So this is the only way we can actually measure the purity and or which isomer we have. Now, we don't know exactly which isomer we have. All we know is that one will do it one direction, one will do it equal and opposite the other direction. Okay. So the basic experiment is if you had an empty tube or one with a chiral molecule, when you put the light through it, you're going to end up with a zero. When you're measuring at the end, nothing has changed. It's going to be where zero was, you're going to measure at zero light, okay? If you have one of the pure enantiomers, it will rotate that plane of light, okay? And that amount that it turns, those angle of which, those degrees of angle that it rotates, is called our observed rotation. And it's typically denoted with an alpha, okay? If the light is rotated clockwise, we're calling this the plus, and that's called dextrorotatory, okay? Dextrorotatory is rotating it in the clockwise direction. And if it rotates in the counterclockwise direction, we call that laborotatory, or have a minus sign, okay? Okay, so that being said, does that mean that R always rotates positive? No. There is no theoretical reason why an RS does one or the other. You have to measure it. So if you have an R compound and you measure it and it might go counterclockwise rotation of 30 degrees, now you get a pure S and you measure it, it's going to be positive rotation 30 degrees. Okay, there's no, you cannot say that, oh, it's R, it's going to be a plus rotation, a dextrorotatory rotation. So unfortunately, you just have to measure it. Okay, so when we measure this, it's very sensitive to things like concentration, the amount of sample that interacts with light, the temperature, and the type of light we use. So when we have these rotations, we actually have to specify what kind of concentration we have, how much of, how long a length it had time to interact with that light, the wavelength of light, because higher wavelengths and lower wavelengths can change it slightly. The solvent can change it. If the solvent is interacting with the compound, that'll change it. In fact, even temperature can change it. Temperature can make the molecule move faster, and it can actually go from being a positive to negative if you measure it at a different temperature. So we always have to note the temperature when we're doing these optical rotation measurements. Okay, so that brings us down to how we would do this, okay? So that was an observed rotation, just looking at how much it went. But now to compare our results to other people's results, we have to do what we call specific rotation. And specific rotation notes the temperature and is set by a specific concentration and diameter, okay? So we take into account the temperature, and notice when we write this here, our specific rotation is in this bracket here. This is would be just our observed rotation. But because we have it in a bracket and we're denoting our wavelength of light, most of the time it's what we call the sodium D line, and it's just a D. And we have the temperature here in degrees Celsius. So it's usually something like 20. You'll see 20 there. Okay. And then we have what we have related to it is that's the measured rotation or the observed rotation. This is the length of the cell. Most of the time when we do this, it's 10 centimeters or 1 decimeter. And then we have the concentration in grams per milliliter. Most of the time we have 1 gram per 100 milliliters. So that's the most common way to measure this. And so we can look at these and I can compare my results to your results to somebody else's results by taking into account these things. So our specific rotations will be the same, even though our observed rotations could be different. Okay. So like I said before, there's no straightforward correlation between R and S and whether or not it's plus and minus. But what is true is if we have a pure enantiomer here and we measure it to be our specific rotation as negative, which means it's counterclockwise, at 23.1 degrees, then its pure enantiomer is going to be exactly the opposite. It's going to be plus 120 degrees. So it's rotated the light clockwise. Okay. So that's if they are pure. Okay. And that's because the molecule that's rotating counterclockwise is the only one available. And so it can only rotate that way. What if you mix them together? What would happen? I bet that's going to change our number a bit. Okay. So, but the temperature is also important. Some molecules, that as you heat them up, they have different bonding available to them. So this aminosuccinic acid here can hydrogen bond to itself and others. But as you heat it up, its interaction with the solvent changes it a little bit. And so it goes from being rotating it counterclockwise at 20 degrees to rotating it clockwise at 100 degrees. So that's why we always have to look at that temperature. Okay, and so the next is what we call a racemic mixture. Okay, so if we had a 1-to-1 mixture of the R and the S, the rotation goes to 0. Okay, let's think about that. All right, so if you have the R and it's rotating light in this direction here, and it's going down this 10 centimeter path and it's starting to rotate the light down that much, okay? And then you have equal amount of the other isomer, and as it's rotating here, it's gonna rotate light this way. So the R is gonna rotate it this way, the S is gonna rotate it back, R, S, R, S, R, S. By the end of the thing, it hasn't rotated at all. So if you have an equal mixture of 2 enantiomers, you have 0 optical activity. And when you have that 0 optical activity in something you know is chiral, we typically note that as the mixture, which is the plus and minus, meaning it rotates at plus, then minus, and it ends up being a net 0. And that mixture is what we call a racemic mixture. Okay. So we're kind of buttoned up here on 10:50, so I don't want to run late, but we will pick up here. So if we have a racemic mixture, that means we have a way to define having maybe not 50-50 mixtures, and that's where we're going to pick up on Friday before our class activity. Any questions about RNS or how to assign RNS? And again, we're going to go over that on Friday again, or how we actually prove to ourselves that we have a chiral center by using optical activity. Come on, there's 25 of you out there. Somebody's got to have a question.
Hi, Dr. Irving. I actually did have a quick question about the slide where you're saying there's 12 different ways to draw the S2 butanol.
Yes.
So I think it was that middle example,
Hmm.
the way things were numbered there. It's I could see how they're going in that clockwise position, but it seemed like um, the fourth priority, that hydrogen, was kind of skipped over in numbering. So
So this one in the middle,
um, one row down to the left.
one row down to my left.
Yes, yeah. I guess the first one of the row. Yeah, that one.
All right, so let's look at that one again. Okay, and so the cool thing is our hydrogen is facing back. So all we have to do is look at the molecule in this direction. So this is little I. So we're looking at it, the chiral carbon here, and now we have to assign our priority to the other ones, right? So we know our oxygen is 1, we know this is 2, and we know this is 3, and our hydrogen is always 4, right? So that's how we've assigned it. And again, we're looking from it down this bond right here, okay? So you want to look at it so that hydrogen is behind that carbon, that four priorities behind that carbon. And when we do that, we have it going in this direction here. So you can imagine it's going in this direction as we're looking down that thing, down that bond. And so this is counterclockwise. So it should be S.
Okay.
Okay. Does that
Okay.
make
Yeah, yeah. That makes more sense. Thank you.
And we can do that same kind of thing here where this is 1, this is 2, this is 3, and this is 4, right? And so if we're looking down this, and again, this is behind here, we're going 1 and 2 and 3, and it is still going counterclockwise. It's still S.
Okay.
Okay.
Gotcha. Thank you.
Practice on a few of these things. Some of them you have to actually rotate the molecule and assign, and then look for R and S. Okay.
All right. Thanks.
Any other questions? Oh, let me go ahead and stop recording. And